Hi ladies and gentlemen, this is Ms. Cook and we're going to continue our work in Chapter 9 and we're going to be running a full hypothesis test today. That is in fact our learning target for today, performing a significance test about a population proportion. In 2014, to save money, Flint city officials switched the water supply from the Detroit water system to the Flint River. The following years became a battle in Flint between residents raising concerns about the safety of their tap water and government officials who insisted it was fine. Today, we will simulate the investigation of Flint's water that was performed by outside researchers at Virginia Tech. We will perform a significance test to see if there is convincing evidence that the proportion of homes in Flint with high lead content in their water supply passes the EPA threshold for safety. In 2014, Flint city officials celebrate as they cut costs by switching the water supply from Detroit to the Flint River. In late 2014 and early 2015, residents began voicing concerns about declining water quality and their concerns for safety, especially for their children. In 2015, the mayor drinks tap water on local television to prove that the water is safe. The mayor also talked about how all of his neighbors also felt like their water was safe. But because of the concern raised by other citizens, outside investigators start testing Flint's water systems. The reason that researchers thought that the new water from the Flint River was problematic was because it was running through old lead pipes, and lead does have a tendency to deteriorate and dissolve into the water. One of the main concerns was when children were ingesting the lead from these old pipes, it can very significantly hurt brain development. It's very easy to take for granted having clean water. But as you can see from the pictures, there was some evidence, namely the way that the water looked, the way that the water smelled, that it was unsafe. But was it statistically significant evidence? And that's what our hypothesis test is going to do for us. Using a random number generator, you're going to select 5 different numbers between 1 and 1,000. And from the numbers that you get, you're going to look up on the spreadsheet having the lead content. You're going to look up the values of lead in each of the different homes represented in the list of 1,000. For each home, you're going to record whether there was a high lead level, meaning greater than 15 parts per billion, or a low lead level at less than or equal to 15 parts per billion. Write an H for high lead level and an L for a low lead level on the lines below. Here's a small excerpt from the table. So if your random number generator, again between 1 and 1,000, randomly picks out the number 633, then you would have a lead level of 7.8. 7.8 is less than the 15 benchmark, so we would enter on our list a low. If in fact you had selected 634, then that would be a lead level of 61.2 in that household, and then you would register a high. So what I would like for you to do is go to the spreadsheet that is linked in Canvas and find the five lead levels associated with the 5 houses that you randomly picked using your random number generator, again, between 1 and 1,000. Once you have recorded whether it's a low or a high level of lead, then turn the video back on to continue on. From the numbers I was able to randomly select on my calculator, I ended up with these results. So I had 4 homes that had low lead levels and 1 that had a high lead level. If we were together, we would accumulate all of our class data. So let's assume for a minute that we have 30 students who each took 5 homes from the list of the population of lead data, and that would mean we would have a sample of 150 total values. So that 150 would be split between low and high lead level homes. So from that 150, let's say that in our class we had 126 low lead homes and we had 24 high lead homes, again combining to a total of 150. So from this value we would be able to calculate our sample proportion. Sample proportion would be, and remember what we're doing is of high lead homes, so it would be 24 out of 150, which would give us 0.16. And that is our sample proportion of high lead homes in Flint. According to EPA regulations, if more than 10% of homes in a city have high lead content in their water, and that is greater than 15 parts per billion, that's considered high, then the city's water supply would be deemed unsafe. Based on the sample in our class, is there convincing evidence that the water system in Flint is unsafe? We start with what we're trying to do, which is to test a claim. The claim is captured in our hypotheses. The null hypothesis, which is the status quo or the original claim, so what we're saying is in Flint, the proportion of homes with high lead water is going to be 10% or less. The alternative hypothesis is going to say it is more than that. We list what our parameter of interest is, or what does P represent. And in this case, P represents the true proportion of Flint homes with high lead water. We always need to indicate the significance level, and in this case, our alpha is 0.05 or 5%. And although we don't need to include the sample statistic in our state, we are going to be using it when we're checking conditions under plan, so we'll go ahead and write it out right here, and this is what we calculated already. Out of 150 homes, 24 of them had high lead level, which gives us a 0.16 proportion. The name of the procedure is one sample z-test for P, which means we're only going to be taking one sample. We're not comparing two samples. It's going to be a z-test, meaning it goes with the normal procedures, the table A and the normal CDF, and the parameter of interest is the population proportion. Next, we're going to check conditions. The first one that we're going to check is random. And this is where we explicitly state that 150 households were randomly selected. The reason that we always check random is because we want to be able to generalize to the population. The next condition that we're going to check is the 10% rule. This is the one that's associated with independence and that allows us to use our standard deviation formula. And what we want to make sure of is that our sample is not too big, because it can be no larger than 10% of our population. In this case, our sample size is 150, and we know that there are at least 40,000 households in Flint. And the reason that we check this condition is because we are sampling without replacement, and we want to make sure that that's not going to take away the independence of the random variable. The last condition that we're going to check is large counts. And that is where we need to make sure that the number of successes and the number of failures is at least 10. So we're going to do n times p, and this has got to be, well, this results in 15, which is greater than 10. The number of failures or low-level households is going to be n times 1 minus p, which gives us 135, which is also greater than or equal to 10. And the reason that we check this condition is because we want the sampling distribution of p hat to be approximately normal. Once we've checked conditions, we're going to write down the general formula. And the general formula is going to be of the test statistic. So it looks kind of like a z-score, but it's what we call the test statistic. It could be z, and in this case it is, but the general formula, we're just going to generically call it the test statistic. And it's going to be the statistic minus the parameter over the standard deviation of the statistic. The specific formula is going to be z is equal to our statistic, which is p hat, minus the parameter, which is p, divided by, and the standard deviation formula that we've been using, p times 1 minus p over n square rooted. Next thing that we're going to do is plug in the values. And I think I'm going to need a little bit more space here. So we're going to have our sample value minus our claim value, and then 0.10 times 0.90 over our sample size 150. This is going to give us a z-score of positive 2.45. Now let's draw our normal curve. We need to do our sketch and shade. Our mean is 0.10. We've got our standard deviation that we just calculated, and our sample value, sample statistic, is somewhere above the mean. And of course, then we're going to shade to that right-hand side, that greater than side, because that's what we're suspicious of, is that the amount of lead is higher than our hypothesis value. So our test statistic, or the z value, is 2.45. And at this point, we're either going to go to table A, or we are going to use normal CDF to get the p-value. So we end up with a p-value of 0.007, which is a very small value. Last of all, we've got our conclude. And the way that we write it up, we need to make sure that we're interpreting the p-value in context so that it's very clear we have an understanding of what it means. So we're going to start out by reminding our reader and ourselves that we assumed that the null hypothesis was true to begin with. That was our beginning assumption. And then we interpret the p-value as a probability. And it's a probability of getting a sample value like the one that we got, or more extreme. In this case, because we're on the right-hand side, it's of 0.16 or greater. And we always need to remember that we need to include a conclusion. And in this case, because our p-value of 0.007 is less than our alpha of 0.05, we reject the null hypothesis. And then we finish up by saying that we do have convincing evidence that Flint's water supply is unsafe. A Virginia Tech study randomly sampled water from 252 homes in Flint. Of those, 42 had high lead content, giving a sample proportion of 0.17. Compared to our class data, does this study give more or less convincing evidence of an unsafe water supply in Flint? And what makes you say that? There are a couple of different things at play here that make the 0.17 more convincing evidence. The first is that the p-hat value is even further to the right or further away from the claim value of 0.10. And the second reason is that although we had a pretty decent sample size of 150, 252 is an even larger sample size, giving us more accurate information when we're trying to calculate a p-value. So the four-step process needs to include the state, the plan, the do, and the conclude. The state, we're going to start out, we wish to test a claim. We're going to include the two hypotheses in context, which means the null hypothesis, which is an equation, and the alternative hypothesis, which is an inequality. And then we explain what the parameter is in the context of the question. We also provide our alpha level in the state. Under the plan, we're going to name the type of procedure, and then we're going to check the conditions. Do, We're going to provide the general and specific formulas, sketch and shade, calculate the test statistic, and then determine the p-value using either table A or using normal CDF. And then last of all, in the conclude, we're going to interpret the p-value and we're going to draw a conclusion. And the conclusion is always either going to be a reject the null hypothesis or fail to reject the null hypothesis. We never accept, just like in a court of law, we can either find someone guilty or not guilty, meaning we have enough evidence to convict them and find them guilty, or we do not have enough evidence to find them guilty, but we never declare them innocent. The test statistic is calculated by the sample statistic minus the population parameter, but the one that was used in the null hypothesis. And that's going to be divided by the standard deviation of the statistic. The specific formula is shown there. And when we have a one-sided test, this is exactly what we're going to do. When we have a two-sided test, and you'll see what that looks like in the Check Your Understanding question. When we have a two-sided test, we're going to double the p-value or find the p-value using the test statistic, but then multiply by 2, because we're going to have a probability on the left-hand side and a probability on the right-hand side that we need to add together and then compare that value against alpha. That's it for the lesson. I would like you to work on the Check Your Understanding question and then check your work when you're done. Make sure that everything is included as we have in our box of important information. If you have any questions, bring them to class.